Okay, so full disclosure, you are now being recorded.
Woo!
All right, starting off for today. First thing I want to do, we need to finish up the outline on reaction energy and reaction rates. It shouldn't take you long. If you look at it, it's only like a page, and it's a little bit on the back side. Hopefully that we get that done, like I said, in the next half hour. Then we will get into the data collection for your types of chemical reactions lab. We'll talk about that more when we get there, okay? And if you have time left, we can work on analysis questions. Although, if we look at the calendar, tomorrow, first, I moved your quiz from today to tomorrow. Okay, we'll have all the information done by the end of the period today. So quiz tomorrow at the beginning of the period. It is open note. Okay, let's go.
Are all the PowerPoints they show in class on the
Yes. So quiz tomorrow in class. It is open note. We will be down in the library tomorrow, so you can go directly to the library. I'll put the sign on the door. Okay? Because after the quiz, we will discuss details regarding the formal lab report. Formal lab report will be written off of the lab that we do today in class. We'll talk about details. Then, any remaining time that we have, which should be a decent amount, you can start working on your lab report down in the library. Monday, if you work on the lab report over the weekend, come back on Monday, ask me questions. Lab report is due on Tuesday of next week. Okay? So if you work on it over the weekend, come in Monday. If you have questions, we'll answer those questions. You can call me, you can fix it Monday, bring it back on Tuesday. Right, so that is our plan for the next couple of days. Good there? Okay.
Yes.
For the sake of Christina, because we're recording class, what I will do is, on today's date, so on the Thursday the 9th, I have taken short little videos of all of the experiments, all 4 parts of the experiment that we're doing today. I will post them online so she can watch them. But if you guys miss a part or something like that, you don't finish it, you can go online and you can watch what happens there as well, so you can see what happens, you can make your observations, just in case you need to go back and look at them or whatever. So I'll have those posted probably tomorrow sometime, I would say. Okay. Good there? The last part of this introduction to chemical reactions section that we've been working on deals with reaction energy and reaction rates. And if you look at your outline, the top part, Roman numeral number 1, hopefully are things that we can answer pretty quickly. So first, Roman numeral 1, letter A, says exothermic. Energy released as heat. Okay? And then underneath exothermic, we have exergonic, which is energy released as something other than heat. Usually it's light. Okay? Usually that means it's light. Now, Julia, just because you asked, if something's releasing both heat and light, excuse me, like a fire or something like that, generally we just refer to that as exothermic. Okay? But something like a Halloween glow stick, it's a chemical reaction. It releases light.
Don't you like crack something?
Right, and then by cracking something, you mix the chemicals that are inside of there, and it releases light. It releases energy, but it's in the form of light, but generally not too much heat. Your Halloween glow stick doesn't get hot. So that would be more of like an exergonic reaction, where it's releasing energy as light as opposed to heat. Okay? Yes, sir. Sure. Let's do the definitions next, okay? So for Roman numeral 1, part B, right, heat is added to a substance. We refer to that as what? Endothermic, okay? And then underneath that, we refer to it as an endergonic reaction, where we're adding energy in the form of something other than heat. So 2 good examples. 1, photosynthesis. Okay? Photosynthesis, plants use light from the sun to start that reaction. It ends up making oxygen and glucose. Okay? The other one, Kevin, you ever get a filling at the dentist? Okay, then this may not work for you. Okay, but yeah.
that's what they do to put brackets on it.
Yeah, like the cement that they use they mix some chemicals together, but then the little light pen, it looks like a blue light. It's mostly ultraviolet.
They
but
tell
it
you
looks
not
blue.
to look at it.
Yeah, they tell you not to look at it. But that's adding light energy to those substances, and that causes a reaction that turns them into like bonding thing.
And I guess endothermic would be like.
Yeah, endothermic could be a cooking process, definitely. Yeah, so we're adding, that's something where, yes, cooking is a really good example of an endothermic process. So, yes,
What about like a tanning bed?
Yeah, I guess, a tanning bed would be an endergonic reaction because, or just tanning in general is an endergonic reaction because the light causes the chemicals in your skin to change. Yeah, so, yeah. How do you go?
Kind of go ahead now. Are we done with that? Are we done with that topic?
You tell me, are we done with that topic?
Okay.
Okay. Go ahead.
So on the next slide,
Yep.
it says it talks about the reactants and the heat is released and it's
Yep.
going down, and that is the exothermic, and then
Okay.
it's going up, it's an endothermic.
So let me talk. Let's do this. Okay. So for those of you that are following along, if you weren't following Hallie along, please do it now. Right underneath the definitions of exothermic and endothermic, okay, there are these two pictures. One of these pictures represents an exothermic reaction. One of these pictures represents an endothermic reaction. Okay. The obvious is that one of them says heat released and one of them says heat absorbed. Okay. But take a minute, talk to the people around you, and explain to me which one is exothermic and which one is endothermic, other than the fact that one says heat released and one says heat absorbed. Talk. Go.
First one is exothermic because endothermic reactions have
Oh yeah, because the heat turns its losing.
when it's being
Well, when it's absorbing, it creates more.
It may not. Yeah, it may not be.
When it absorbs heat, it
All right. Let's discuss. Okay. So the picture on the left is which? This is the exothermic reaction, the one that's on the left. Okay. Other than the fact that it says heat released right here, right? How can we tell if this is an exothermic reaction? Kelly, go ahead.
Because as you release heat, you're giving off energy
How do you know that from this picture?
because it's going down, and
What's going down?
after the hill,
Okay.
after the reactant, like what do you call it, like the climax hill, maybe? I mean,
If we look, so Hallie, what is our y-axis labeled as in this graph?
oh, that's complex.
Right. So if we start here, right, at this level, and we end up down here, right, what's happened to the energy from our start to our finish? It decreased, right? So where does that energy have to go?
Why is it going up, Chris? Because
Okay.
it's building up energy to release?
So let's talk about that, okay? This little section right here, if you look from your graph, you can see that first the energy goes up, then we get that big crash downwards. Okay? We refer to this section here as the activation energy.
So like when you crack the glow stick, that's like
Right.
that's when it goes up.
Before, yes,
That's why it's the brightest when you crank.
right. So reactions, even exothermic ones, don't always occur just by themselves. Let's look at an example that we're going to look at, that you're going to see later in lab. Okay, your Bunsen burner. Okay, in your Bunsen burner, methane comes out of the gas jet. Okay, it combines with oxygen to make two products. What two products does it make?
Two H2O.
H2O and carbon dioxide. And Julie, you're right. Here. Okay, nope. Sorry, not the last one. The two. No. Yeah, that's right.
The perfect ratio is 1 to 2.
Yep. In this case, the perfect ratio between oxygen and methane is 1 to 2. And actually, Ryan, that's what we're going to get into starting next week with stoichiometry. We start looking at the relationships between the reactants and products and stuff like that. Okay? Now, here, just because you turn the gas jet on, does that automatically start producing water and carbon dioxide? No. Well, what do you have to do to get that reaction started? Jen, what is the match adding to that situation? It's adding heat, right, or energy in the form of heat, okay? That equates to this little section right here, okay? This reaction won't start on its own. Just because you mix methane and oxygen together doesn't mean they automatically start combusting, okay?
Oh, the match is exothermic.
Right. The match is adding energy to these two, and as a result, we end up forming the two products.
And what about the endothermic?
Well, hold on. Let's finish this one up for a second. Okay. If we take a look here, right, I think we all got the gist that when we're looking at this reaction, all the pieces parts that are there at the beginning end up at the end, right? That's the whole idea of balancing equation, the conservation of mass, and all that stuff we talked about earlier last week. Okay. But it's arranged differently. So before we make water and carbon dioxide, what do we have to do to these two? We got to split these up into pieces first. Will the methane and the oxygen split up on their own into individual carbon and oxygen and hydrogen atoms? No, right? Because they're already kind of stable. That's why they formed this compound to begin with. Okay? But by splitting them up, now they can rearrange themselves into the water and the carbon dioxide, and that rearranging of those elements into water and carbon dioxide releases more energy than we put into it to begin with. So overall, we give off more energy than we put into it. Okay? Now, Hallie, on the other side, obviously, I hope we can gather that this one is the endothermic reaction. Okay? If we take a look at this equation, the combustion of the methane, could we take apart the water and the carbon dioxide and put them back together in the form of methane and oxygen?
Yeah.
Could, right? Because all the pieces are there, right? But what do we need to split these up first? You need even more energy, right? So technically here, the activation energy is really big because the water and the carbon dioxide don't like to be split up. They're pretty stable that way. Now, so you put a bunch of energy in and you split them all apart.
And you get less hot.
Putting them back together as methane and oxygen will release some energy, but how does it compare to the energy we had to put in to begin with?
It has to be so much better.
Well, in this case, how does the energy they give off?
The more energy, the less hot.
So, in the endothermic reaction here, right?
Yeah.
Okay? I gotta make sure that I point to the screen because Christine is watching at home. You know, she doesn't know like how I'm pointing at it. In this part, right? Oop, not that part. This part. Okay? That part equates to splitting up these water and carbon dioxide molecules.
And what's the downward part?
So the downward part relates to these four hydrogens that I split up from the water, these two oxygens, this carbon, and these two oxygens here, forming back together into this and this, right? If we reverse this reaction and went the other way. Okay? Does that make sense?
So the yellow is getting red too, kind of.
The yellow is splitting up this and this. Will water and carbon dioxide split up on their own?
Yeah, but then the
No.
red isn't
No.
moving. Actually,
Right. The red is how much energy gets released. This red is how much energy gets released when these individual atoms, which we split all of them up, come back together and form this. But we got to put more energy into it than we get out of it. Right?
How come it takes more to split up the case?
Which side is going to be more stable, Hallie?
The right side.
The right side. Right?
Oh, okay.
That's why. Okay. The other example I used in class was like, okay, let's say for whatever reason you made a big, huge pirate ship out of Legos. Okay? Big, huge pirate ship out of Legos. What? Yeah, I mean, that would be pretty awesome. So, but let's say for some reason you really wanted to just make one big, huge, tall stack of Legos. Okay? Not like a building, just one big, huge, tall stack. Could you take apart your pirate ship and turn it into a big, huge stack?
Yeah, but it costs more energy to go.
Right. The time and energy you'd have to put into taking the pirate ship all apart, right, and then putting it back together in that stack, that's going to be more like an endothermic reaction. You don't get as much out of it as you put into it, right? So overall, it was harder to split up the pirate ship than it was to put the stack back together.
So the final result more stable?
No, less stable.
So then the exo, so it'd be the middle.
Right. So
How does it give off energy like once they have split apart?
because, Sadie, remember that atoms by themselves, like oxygen by itself with 6 valence electrons, is an unstable situation. It's not going to sit there by itself with 6 valence electrons. It's going to find something, okay? In this reaction here, going from the left to the right, if we split these oxygens here, these oxygens, right, into 4 separate oxygen atoms, the next thing it finds are these 4 separate hydrogen atoms that originally came from over here. They join together to form water because water is more stable than the 2 hydrogens and the 1 oxygen by itself. Same thing going the other direction. If we take water out of these two, if we take oxygen out of these 2 compounds, it's going to find something. So it's not going to stay that way. It so happens that it finds another oxygen and forms that O2 molecule. Okay. Julia, go ahead.
Doesn't methane and oxygen only meet when they hit the air?
Yeah.
So like, it's hard to just make it. Would you say?
Well,
Like,
the whole point of this being, just because you mix methane and oxygen together doesn't mean they're automatically going to start forming these 2 products, right? That's where this whole idea of activation energy comes in. They don't start forming these 2 products until you bring the match in and provide them with this little boost to get them over the hill, right? Because methane and oxygen, they're already somewhat stable. That's why they're in a compound to begin with.
so say like filled like a room with methane and it had air in it too, and you lit a match with water and carbon dioxide, just start creating.
Yep.
That'd be awesome.
I mean, now, but Julia, I can't remember if we talked about it in this class or not. If you look, right, methane and oxygen are both gases. Gases take up a lot more space than liquids do, right? So even if you had a full room full of methane and oxygen, you won't
Fill up with water.
right. You won't fill up the room with water, right? Does that make sense?
Yeah.
Okay, so that's something you have to think about. Okay. Yes.
What about the reaction between sodium and H2O?
What about it?
Would that be classified as an exogenous reaction?
Sure.
But it doesn't really take in energy, does it? Like, since
It doesn't need very
it's
much.
more it's like
So in that case,
as soon as you drop it in, it just sort of
right.
flows.
In that case, the activation energy is very, very low. So basically, the act of dropping it into no, it's very exothermic. But even exothermic reactions need activation energy, right? Or Kevin, lighting a match, right? The activation energy is provided simply from the heat that you create by dragging it across the matchbox. In the case of those reactants, the match head and the oxygen in the room, that heat that's created just by dragging it across is enough of an activation energy to start the reaction.
What's that energy that's being taken into the reaction? So water.
Basically just the idea of them being together, because the activation energy for that is so low, while sodium is so unstable the way that it is. All right, these 4 pictures appear on your outline right underneath those 2 bigger pictures. Sorry, 5 pictures, okay? The reason I said those 4 pictures is because on your outline, I would like you to take the 4th one, right, number 4 from the left, okay, this one, and pretend like it's just not even there. Just get rid of it.
Would that be
No.
like be
because it makes the answer harder to figure out.
But so it'll be a competition.
Yes. It would lead to,
And
it would
we'd be
lead,
yelling
it
at
would lead
you.
to good questions by your inquisitive minds that I don't want to answer right now.
Well, okay.
Glad we got that on. Glad we
Well,
got
would that
that
be
on
EXO?
record. It is EXO.
Okay.
All right. So first, there are 2 exothermic reactions and 2 endothermic reactions of the remaining 4 pictures. Actually, Hallie, for next year, I'm going to get rid of this picture and just leave the 4 that are up there now. So I just decided I was going to manually do that this year. So, of these 4 remaining pictures, there are 2 endothermic reactions and 2 exothermic reactions. Okay? Hopefully, by looking at those pictures, you can see that the first 2 are endothermic reactions, and the last 2 are exothermic reactions. Okay. Questions there? Okay, now, good.
Like, does it matter, like with the different graphs, that because of the different elements that have like separated them?
Yes. So, see, the next question, okay? Underneath those pictures, there was a little question that says, which of the products will be the most stable? How do you know? I'm going to change that question. Next year I'm going to change it for the outline, but now you're going to change it manually. Okay? So instead of saying which of the products is the most stable, I want that question to read, which of these reactions is the most likely to occur? And we can keep the how do you know parts. So change that question from which of the products is the most stable to which of these reactions is most likely to occur. And once you've done that, I want you to turn around and talk to the people next to you and answer that question. Which of those 4 reactions shown will be the most likely to occur? Discuss. Go.
The third one.
That's what I said too. Is it the third one?
The third one also because like
Yeah, it's a really stable.
it starts to
Plus it just looks more very stuff.
the other thing is like endothermic goes from like stable to unstable, and so the closer the reaction level is to the product level, the more energy is needed to create the reaction.
That's the answer to this question. So.
Oh,
How do you
I was actually like looking at that just before you.
All right, so let's discuss.
how
Yes.
I feel so smart
I feel like
when I should.
Which one is that?
yeah, you said this.
No, the first 2 are endo, and the last 2 are exo.
That this one.
So, yeah. Sorry, I meant disregarding that.
So I was right. Well, I was wrong.
Okay. So, the most likely reaction to occur is this one. Okay. I heard a lot of good discussion as far as why this is the most there's 2 things that you could look at to justify that this reaction is the most likely to occur. Julia, what's one thing to look at?
Activation level is lower.
So the activation energy is not very high. All right. What's the other thing we might look at, Josh?
Is it because of the fact that it's exothermic and exothermic goes from non-stable to stable?
Why? But this one is also exothermic, right?
Because it uses less energy to activate.
So the activation energy isn't very high. That's one reason. Okay. But there's another reason too we could look at. All right. Kevin, go ahead.
Because the energy levels of the reaction and the product are like vastly different.
If we look at where the energy was of the reactants and where the product energy level ends up, it's far greater in this reaction than it is in this reaction. Okay? Which means that the products in reaction number 3 are much more stable than the reactants as compared to this one. Okay? If we go ahead, Julie.
So the activation level is always the same.
No. Like here, okay, Julia, in reaction number 5.
It's always at like this
Right.
part. Like it peaks at this part every time.
Well, there's always some peak.
It takes almost as much for the glass to take almost as much energy as it does the weight get out.
Right.
And so
These products, or these reactants in this reaction, are already pretty stable because their energy levels are very low. So if you want to make something new, to split these products up is a pretty big jump. And then the gain in stability, or the loss of energy that you experience going back down the hill, isn't that much different from where you start.
So, how would you explain the second?
So the difference in the energy level of the reactants and the products is not very big at all. So there isn't much more stability in the products than there were in the reactants. Does that make sense? Okay. Sadie, is that what you wanted to ask her?
Well, I was gonna ask like on the reactants, how like some start lower and then some are higher. What does that mean?
That means that like in this reaction, these reactants are already pretty stable to begin with. That's why the activation energy is so big, because it takes a lot of energy to split them up, because they're already pretty happy the way they are. Whereas in here, in this reaction, right, being higher up on the y-axis, those reactants have kind of a lot of energy anyway, so it doesn't take that much to split them apart, because they're already kind of unstable. Okay. Good there?
So the reactant products are smaller.
For which one? The reactants and the products are different.
Oh.
Because the drop is much bigger in number 3 than it is in number 5. Does that make sense, Alex?
So,
We're looking at the difference between where the reactants start and where the products end up.
okay.
Okay? And in this one, in number 3, the difference is much greater than it is in here in number 5. Okay. Kevin, go ahead.
Is digestion an exogonic reaction?
Exothermic.
That's different.
Yeah.
Okay.
Because it gives off heat. That's why you're.
I didn't know that, but like you have kinetic energy from the.
That's where you get your kinetic energy from.
So,
But you're also a warm-blooded animal. You maintain your body temperature from the reactions that are going on in your body.
Like when you sweat.
Well, when you sweat, the reactions that are occurring in your body, it's the same reactions whether you're sitting, sleeping, and your heart's just beating, or whether you're like running. The reaction is the same because it's releasing energy, but you need a lot more energy to run than you do to sleep.
Yeah.
So that's why your body goes in and starts doing that reaction quicker, but the result of that is how much heat you produce.
Yeah.
You produce more heat because you're doing that reaction more than you are when you're sleeping,
So,
right?
But when you're playing soccer, do you like think of all this?
No.
No. You're
I
just
think about, oh
thinking.
crap, that guy's over there and he's faster than me and I better get that sword. Like, my body. So that's it.
are people thinking about that when they play soccer?
no.
I imagine it might be, but I'm not.
No. Okay.
Yes, Alex.
So, why would it not be number 4?
That's why I get rid of number 4.
Because,
It makes this conversation a lot harder.
oh, is it because of the differences?
Yeah.
Aren't they the same?
Yeah.
Like, I think the only reason why it would be like,
That's why I got rid of it, 'cause it just makes this conversation a lot harder to handle.
really,
So,
I just say.
Yeah, it's
but the difference in the levels of the reactants and the products in 3 and 5 are much more dramatically different than they are in 4.
But would number 4 still be like?
I would say number 3 is still probably the answer to that question.
Yeah.
That's my.
okay. Can we go on?
All right, so
It's been over half an hour.
I know. As if I didn't know that was going to
Be
happen.
kind.
By the way, just to drag this out a little hard, in class the other day we were talking about the types of reactions. Did I discuss that the one reaction is like the Taylor Swift song?
Yes, we're talking about.
After school on Tuesday, went to the dentist, sat down in the dentist
Yeah,
chair.
with that song.
First song that comes on the radio, Taylor Swift.
Are you laughing?
You Belong With Me. Yeah, I was trying not to laugh while she was cleaning my teeth.
She's like, what?
I was like, no.
What'd she say?
No, she didn't notice. But I did tell her a little bit. But as we discussed, extremely catchy. Dude, what's going on back here?
Just my land.
Why are you so
I didn't know people.
All right. As far as how quickly reactions occur, we just discussed the idea of why reactions occur, or which reactions are more likely to occur based on energy levels and stuff like that. But as far as how fast those reactions occur, there's a couple of things we can do to speed them up or slow them down. First, temperature. How does temperature affect the rate of the reaction generally? Generally, if we heat up the reaction,
the higher temperature?
higher temperature means the reactions go faster, generally. Why? What does raising the temperature do?
Just get some energy.
Adding energy. What do those particles do more as we add? They move more, so they run into each other more often. There we go. Okay. Along with this, right? Stirring. If we stir something or agitate or shake something, right? Yes, but what does shaking or stirring do to the particles in that mixture? Makes them go faster. Is that basically the same thing as temperature?
Yeah.
Pretty much is. Okay? So stirring and temperature basically have the same effect because they're basically doing the same thing.
My mom was making spaghetti sauce, and my sister was supposed to watch it when she was picking me up at school. And my sister didn't watch it and stir it at all. So there's burnt and I had to scrub the bottom of that pot.
Why isn't she scrubbing the
It's
pot?
because it was my job. Because we switch jobs every month, and I was pasta pans. Yeah.
All right.
Yeah.
Next, surface area. Large surface area speeds up the reaction. Large surface area equates to making something like into a powder, right? If you talk about dissolving sugar, if you try and dissolve a sugar cube versus like a spoonful of granulated sugar, right? The granulated sugar is going to dissolve faster because there's more surface area there. Each one of those little pieces can come in contact with the water, whereas in the sugar cube, it's only the outside of the cube. Okay?
That reminds me, I'm having a tea party on Sundays.
Yes.
Is it kind of just like how those big pile of snow mounds are like outside?
They take a long time to melt. Yes. Sadie, great example. So. All right, last. Like the big snow mountains, the parking lot at the mall or something like that lasts for a long time.
Wait, then you have the large surface area starts up in the reaction.
Even though that's actually a reaction, what's happening?
Like gases
Melt.
that react fast.
Melt.
But then why would the large surface area make it go faster?
Because
They're
the
close
inside,
gas.
because Kelly, the inside of that snow pile doesn't get exposed to the sun and the warm air.
So when they slow down the reaction?
Yeah, because a big snow pile has less surface area.
So why would that? Kelly, you're thinking of big surface area of like big surface. If I think get this right, like for water in your sugar example,
Yeah.
like the water has a bigger surface area for the granulated because they're smaller. Right?
Well, no, because the granulated sugar, it's not like condensed.
Yeah, it's not condensed.
It's like spread out.
So Kelly, there's the big snow pile. Okay? And here is the surface area of that big snow pile. Okay? But if I break this big snow pile up into this pile, and this pile, and this pile, and this pile,
Those ones will melt faster.
okay? Nope. Come on. How much yellow did I draw here versus here? That means it melts faster, right? Because melting is occurring on all of the yellow surfaces, right? This is more surface area, melting occurs
So
quicker.
then why give a ginormous mound and then you have like a little tiny little this like how come this one will melt faster?
Because that one is smaller to begin with. There's not as much snow there that has to melt.
The surface area is larger.
That's true, but the surface area is larger, but you got to do more.
But it has to be like it's not just the surface area.
It's not. The surface area contributes to the rate of reaction, but if you have to get rid of more snow, right, that plays into it as well. Right, go
What
ahead.
if you like connect like that smaller one a little more than the bigger one?
Mhm.
Could that actually affect it too?
Could be, yeah, that could have something to do with it too. The density, because density, remember, Kartik, is like mass over volume, right? So really, if you have a low density, there's a lot of volume, so there's actually air mixed into that. Right? Josh, go ahead.
Will that also affect like the melting point of like anything, like butter or?
It'll affect how quickly things occur. Yeah.
Can we go there now?
No. Finish this. So people stop talking.
Concentration. Stop asking questions. Why do you have to be so curious?
Let's go.
Oh, I get it.
You ask asked the question about the snow. I just said Sadie. That was a really good example.
He's like,
All right, next, concentration of reactants. If we increase the concentration of things, generally they'll go faster. That's the equivalent of being more stuff there.
you what the hell?
This is why this is cross-curricular learning right there. We just used a vocab word within science.
Wait, you had the
All right.
I just learned it today, okay?
Last slide. Okay. There are some chemical factors. Oh, sorry, for the last one. So chemical factors. So first, size of the reactant molecules. Big molecules react more slowly than small molecules.
Like the big pound, big thing of snow is a bigger molecule. And the small one
You can
is
think about it that way.
Which would place the more effect, the size of the molecules or the surface area?
It would really depend on the individual, like how those things measure for those individual things. It's hard to say that one's more important than the other. But surface area is more of a physical thing. It's easier to control than this is. Josh, go ahead.
You put that. What? You put that.
I was looking at that too, but I was too like.
Oh, right on.
If we have like Kool-Aid and we let the Kool-Aid evaporate, we still have the powder at the bottom.
Eventually, yeah. So I mean, if you want to make it go faster, just not put your Kool-Aid on the stove and like boil the water off.
Kool-Aid.
Fill it up with the powder, your mom might not be too happy about that. All right, the last.
Like under her cabinet.
No, it would be in the pot.
Yeah.
So.
Yeah, it would.
So the last chemical factor that we talked about is the catalyst. Okay? A catalyst is a substance that changes the reaction without being consumed or significantly changed. Okay? Here's my best example of what a catalyst is like. Okay? Two students are involved in a verbal confrontation.
So,
Okay? No, they're not fighting. They're just yelling at each other. Verbal confrontation. No. So, because it appears that this verbal confrontation may escalate into a physical confrontation. Okay? So the catalyst, okay, the catalyst to this situation is that guy that stands there. No.
No, he's
No.
making it happen. He's going like, yeah.
Hallie, what you're describing would be a inhibitor, which slows a reaction down. Okay? The catalyst, on the other hand, is the guy that goes, "Oh, did you hear what he said? Oh, are you gonna let him say that to you? Oh my God, I can't hear it." So,
Are you guys gonna fight?
yeah, fight. That's the catalyst, because that guy is not involved in the fight, right? He's not involved in the reaction. He just stands there and makes it all go a little faster. Okay? But Hallie, this is generally what teachers do.
But the catalyst is needed.
What?
But the catalyst is needed.
Say again?
The catalyst is not needed. Because
Like,
that makes sense.
Nobody's
Like,
eating.
that.
Eating?
Yeah, eating.
Right, yeah. He doesn't, the catalyst isn't on like eating? Like that's what you're talking about, right? Like putting food into your mouth and chewing it? Okay. I guess if you want to think about it that way, yes. Okay.
Nobody's chewing on the catalyst.
Being consumed means it's involved in the reaction.
It's like the catalyst is like teeth making any
What if it spreads off?
What?
go with his.
All right.
Reaction.
The last catalyst word I want you to be familiar with is an enzyme. An enzyme is a catalyst. It makes things go either faster or slower, but it's a biological catalyst. It works on metabolic reactions, which are those are reactions in your body. Metabolism. Metabolic refers to the process.
I think we went a little longer.
We did, indeed. Come on.
Wait, so how can it change reaction without being consumed? What is that?
I broke my eraser.
Hallie.
Throw it at something.
I mean, like, I can tell you what a catalyst is chemically, but it doesn't like mean anything. When you're writing an equation for that reaction, the catalyst doesn't show up on the reactant side or the product side. It's not part of the reaction.
It's just like there.
Yeah, it's just there, and it makes it all go a little faster.
But it's not in the.
Can you give us like
But it's not the. One that you'll know.
Yeah.
So, I mean. Can't really think of one that would like make sense to you right now. Okay. So let me think about that one a little bit.
Maybe just like.
Josh, go ahead.
On a test, would we have to explain the difference between a catalyst, inhibitor, and a science?
Maybe between a catalyst and an inhibitor. Because a catalyst speeds up the reaction, whereas an inhibitor slows it down.
Well,
Yeah.
But if it acts like
there's under
how?
That's true. An inhibitor is a specific type of catalyst, one that slows down the reaction.
That'll be actually.
Yes.
Okay, so like in one situation, like what would a catalyst be like in or you go?
A catalyst is generally a compound that
You know,
maybe.
when I used to do that,
Hey,
great.
hey,
He's throwing eraser bits at me.
hey! I'm trying to record this, and I got your petty little argument here. Hey, stop throwing erasers.
We're just making examples. This is how we learn.
Now we got that on tape too. See,
Mr. Freeman.
generally, it's like something. Okay. Today, you're gonna get two powders, okay? And those two powders are gonna don't inhale. Those two powders are gonna mix together and they're gonna form a set of products, two products. The fact that you're gonna first dissolve them in water first, okay? The water doesn't take part in the reaction between those two chemicals. But by dissolving them in water, we increase the surface area, all that stuff, and it makes the reaction go faster. But when you're writing that equation, water doesn't show up anywhere in that equation. Make sense?
So that's a catalyst.
That makes it a catalyst.
Like,